don't have my glasses. Okay, so we're live streaming it on YouTube, and this way we will be able to also have a permanent link for those who cannot join us tonight.
Hi,
so let's just give it a couple more minutes and then we will start. Okay, so I think we can go ahead and get started, and probably more people will be joining us as we go. Thank you so very much, everyone, for joining us tonight. Welcome to our meeting today, which is dedicated to the Mosteller Statistician of the Year Award. But before we talk about that, let me just welcome you in general to the chapter. If you are new to the chapter activities, let me just say a couple of words about who we are. So we are a chapter of the American Statistical Association, which serves New England states. And our goal is to bring together everyone who is interested in any aspect of statistics and data science. And what we do is that we organize a lot of events, which are either educational or professional or social, which allow us to share our common interests in general and get to know our colleagues in the area so that we can go beyond one institution and have contacts and common interests with people who are in this area. So let me show you, I will share a screen for a second and show you the upcoming events that our chapter is going to organize. So by the way, this is the Boston chapter website, and here is the button to join the chapter if you're not a member. So we very much encourage you to do this. I think the membership is just a few dollars, I think $5 or so. And you can become a chapter member even if you are not the member of the American Statistical Association. So some of the upcoming or recent events, either directly sponsored by the chapter or by our colleagues in the area. So there's a Tufts Research and Data Symposium for Food and Nutrition. Today, we're talking about the Mosteller Statistician of the Year Award. Women in Data Science and Statistics Worldwide Conference. This is not something organized by the chapter, but we hope it can be of interest to our community. So we also have a virtual student research symposium on statistics and data science coming soon. We also have a Boston Pharmaceutical Symposium planned for spring 2022, and this will be not one day, but a series of mini presentations spread over a series of days. We also announced the New England Statistics Symposium, which is organized by our colleagues in New England Statistical Society. In the fall, there will be a traveling course on navigating tough conversations in statistical collaborations, and a series of other events later in the year. So this is, in fact, not a full list, so more events are being planned. And so if you are interested in any of these events, or you're interested in hosting events, or you would like us to promote the events that you organize in your area, you're most welcome to contact myself and Kristin Baltrusaitis, who is the program chair of our chapter. So with this, so let me now open the floor and talk about the Statistician of the Year Award. So the Mosteller Statistician of the Year Award is a award presented by the Boston chapter of the ASA every year, and it highlights a distinguished statistician who made exceptional contributions to the field of statistics and who has also shown outstanding service to the statistical community. It started in 1997. So this award was, it started in 1990, and it was given first to Fred Mosteller, who was one of the most eminent statisticians of the last century. He was also a founding chairman of Harvard Statistics Department. And in general, this award is open to individuals from academia, industry, and government, and anyone who made exceptional contributions is eligible to apply. And the award is competitive, so we received several nominations. The planning committee of the chapter votes on the recipient. And so this year, I am absolutely delighted to introduce Dr. Francesca Dominici, who is recipient of this year's Mosteller Statistician of the Year award. So let me say a few words about Francesca. So Dr. Dominici received her PhD in statistics from the University of Padua in Italy. She then did her postdoctoral training with Scott Ziegler and Jonathan Samet at the Bloomberg School of Public Health at Johns Hopkins University. She was appointed assistant professor and eventually promoted to full professor there. And in 2009, Dr. Dominici was recruited to the Harvard T.H. Chan School of Public Health. And she was appointed as Associate Dean of Information Technology and also a Senior Associate Dean for Research. And currently, Dr. Dominici is co-director of the Harvard Data Science Initiative. So in this role as a co-director, Dr. Dominici is building on the collaborations that already exist at the university with the goal to foster and reach a cohesive data science community and try to bring together scholars across different disciplines and schools, very much in the spirit also of the Boston chapter. Dr. Dominici is an elected member of the National Academy of Medicine and of the International Society of Mathematical Statistics. In her research, she leads an interdisciplinary group of scientists who address important questions in environmental health science, climate change, and health policy. She has more than 250 publications and has provided her knowledge to panels with New Jersey Senator Booker, to European Commission, and her suggestions to the scientific community and policy makers had a big impact in terms of understanding the adverse health effects of air pollution, noise pollution, and climate change. And so I am very much looking forward to hear from Dr. Dominici today. Thank you so much for joining us, and thank you everyone who is here in the audience. I look forward to the talk, and congratulations again. Oh, and one thing, so we are presenting a plaque which commemorates this event, which I hope, have you received the plaque?
Yes.
Already? You did, okay, wonderful. So in normal times, we would actually hand the plaque and take a photo. So we will have to do with the Zoom version, but again, my sincere congratulations with the award.
Thank you. Thank you so much, Olga, for the lovely introduction. Thank you very much to the chapter. I am delighted and flattered to just have the word Mosteller anywhere in my my CV. So thank you so much. I'm sorry. I heard that that absent pandemic that would have been a dinner, but I heard that this award is giving every year. So I'm gonna crash the dinner next year with the next award. And I will also bring my plaque along to show it.
Absolutely, absolutely.
So I will definitely do that. Thank you so much for joining during an evening. And I will keep this very light and informal. It's absolutely my delight to share with you my research, but mostly to really highlight the research of my student and postdoctoral fellows, because that's really when I want to give the full credit to them. So I'm going to share my slide. Let's see, one second. Here we go. Okay, all right. So. Perfect. I will be speaking about really my passion, which is leveraging and developing methodology in data science to address extremely important question in environmental policy, which also, as you will see, have been having an intersection in the context of COVID-19. So I am a big advocate that all the most important air policy, air quality policy, and environmental policy and climate change must be informed by data. And actually, I think that in the context of air quality regulation, this has been a perfect example where when the policy changes is informed by data, actually the policy becomes effective. And so what I'm showing in this plot is on the left are the ambient level of the major air pollutants in the air. And you can see in the left that they have been declining steadily over time. We are breathing indeed cleaner air. You can see on the right the skyline of Chicago. On top was the skyline in the 80s, and now it's in the 2020. So this is thanks to the Clean Air Act, where the Clean Air Act said that the Environmental Protection Agency has the mandate to review all of the evidence as whether or not ambient level of air pollution are affecting human health. And if indeed they are, they must lower the national ambient air quality standard. So my role, my job, and I feel also a responsibility, is to gather the largest possible data and bring together scientists to provide evidence as whether or not the current level of air pollution are safe to human health. And if they are not, then we directly inform the Environmental Protection Agency asking to lower the national ambient air quality standard. And that's really what has been resulting really for all of us on breathing cleaner air. So we now have a very specific question. Currently, the national ambient air quality standard for fine particulate matter are very small particles that breathe and penetrate deeply into your airways. The current national ambient air quality standard are set at 12 micrograms per cubic meter. And so we are now asking whether or not there is evidence that there is an increased health risk at level below the national ambient air quality standard. If there is, then by law, by the Clean Air Act, the Environmental Protection Agency has to lower the standard. Also, we want to ask the question of whether or not some population are higher risk than others. So I really believe in data. I spend my entire career really devoted to bring together data as broader as possible. In the United States, as many of you know, although we don't have a national health insurance, we know that the majority of people older than 65 enter into the Medicare system. And so for them, we have claims data and we know a lot of things about them. So this is a large population, is over 97% of people older than 65. So it's around 67 million. We have their individual claims from the year 2000 to 2016. Actually, we now just have purchase data for 2017 and 2018. We know their date of death. We know the date of every single hospital admission and their cause. We have the date of age. We have their age, the day they enter, that becomes eligible to Medicare, their sex, gender, race, and also we know whether or not they're also eligible for Medicaid, which is a surrogate, a proxy for lower socioeconomic status. Very importantly, we have the zip code of residence. So that's really important because I'm going to show you we can augment the data with their exposure to different air pollutants. So one element of what we do, and this is really the work of many people, which I will have the pleasure and delight to recognize at the end of the talk, is really a massive work of harmonizing and integrating heterogeneous sources of data. We have data from health, so that comes from Medicare and Medicaid claims. We have data on environmental exposure to air pollution, but now we have a larger team is also looking at exposure to climate change related events like heat, like exposure to heat, exposure to wildfires. exposure to tropical cyclones. And then we have data about socioeconomic factors, which might act as confounder of the relationship between exposure to air pollution and climate change related exposure and health. So this is a snapshot of this data platform, as I was mentioning. So we curate exposure to environmental exposure, to exposure to air pollution and climate change related factors. We curate these claims data and then curate all of these socioeconomic factors. All of this data comes from government data sources. These are all publicly available. It's just that are really very different, very heterogeneous. And so there is a massive amount of work in harmonizing and linking and curating them. So the first step of all of this is to be able to have a very good assessment of the level of air pollution that every single Medicare enrollee is exposed to. So now this map shows the monitoring station in the United States that measure daily levels of fine particulate matter. This data is also publicly available. You can download it from the EPA website. So as you can see, there are a lot of monitoring stations in the US from which we monitor fine particulate matter. But still, there are areas in the United States where we are not monitoring air pollution really well. And remember, we have claims data, we have health data for every single zip code in the United States. So you can see from this map that there will be some zip codes that are far away from a monitor. So if we want to assess the exposure to air pollution for everyone, for some people we'll be able to measure their pollution level they are exposed to better than others. So the first major contribution, there is a team where there is a contribution of a colleague of mine, Joel Schwartz in the Department of Environmental Health. But actually now there are multiple teams around the United States that what we do, we develop a machine learning and artificial intelligence model to be able to assess with a higher level of accuracy how much pollution we're breathing every day for every single zip code in the United States. Actually, they do it, we are doing it for 1 kilometer to 1 kilometer grid for the entire continental United States. What is the fundamental idea? Okay, the fundamental idea is that we take a lot of imprecise data. So the most important imprecise but rich data is the data that comes from satellite. So now we have satellite images that give us a measure what we call the aerosol optical depth. That is an imprecise measure of air pollution. Then we have weather data, we have output of atmospheric chemistry model, we have data on land use, and then we have the PM2.5 monitoring data. So we develop this neural network and other machine learning, including ensemble learning, where we take all of these measurements, we train the machine on the monitoring data, and then we can estimate the level of pollution of 1 kilometer to 1 kilometer grid. I just want to mention that this is a very active area of research. There are hundreds, maybe more, of investigators around the world that are taking satellite images and atmospheric chemistry model to really estimate how much pollution we are breathing in the United States, but also all around the world. I want to mention my colleague, Marianti. She's a faculty member and associate professor at Columbia University in the Department of Environmental Health, where she's specializing in taking the output of all of these different atmospheric chemistry models that are listed here on this table. Some of these are atmospheric chemistry models, some of these are machine learning models, some of these are a combination. All of them have the objective of estimating how much pollution we are breathing. She's taking all of these models and combining them and averaging them so then we can get the best possible estimate. So this is in one area really that not only estimates ambient level of fine particulate matter, we're estimating ambient level of ozone, of NO2, or now the chemical components of PM2.5 or wildfires. And so it's really give us an opportunity to really assess our risk factors. Now, one of really important paper we published a few years ago, which was led by, at that time, a former PhD student in the lab, was really a landmark study. It was probably, I would guess, the largest study that the New England Journal of Medicine ever published, because this was a study of over 400 million observation. And I know that because I had a fight with the New England Journal of Medicine, because they don't allow to have more than 2 decimal points on their tables. But our estimates were so precise that we needed to report at 3 decimal points. Anyway, that was an interesting observation. So in this study, we really were able to link exposure to fine particulate matter to the health history of 60 million Americans. So this is just a sense of the table. We have 60 million people. And if you focus only on the first line for a moment, on the first row, we see that we have 32 million Americans that were breathing level of fine particulate matter always below 12 microgram per cubic meter. So that's really important, because if we found that among this population, they are having adverse health effect, that means that the current standard of 12 microgram per cubic meter is not safe enough, and that we need to lower the standard. So we really want to have enormous sample size for people that are living in geographical area that, let's say, are breathing clean air, or breathing air that our administration is saying is safe for you, right? So we analyze this data using pretty standard traditional Cox proportional hazard model. So I'm not going to go into the detail of a very standard time to death analysis. It took days to run this model, and I'll tell you a little bit about the computational scalability in a second. What we found is that the horizontal line is placed at an hazard ratio of 7.3. So basically, we found that for every 10 unit increase in long-term exposure to fine particulate matter, we have a 7.3% increase in all-cause mortality on average for everybody. What was really striking is that the Black American have a mortality risk associated with fine particulate matter that was 3 times higher than the national average. And so it was up to 20%. We also have that Asian American, Hispanic American, Native American, male, and for a certain extent, a little bit, the people that are also eligible for Medicaid have a higher risk. So it's interesting that in 2017, to run this analysis, it took, I think, 3 days of the fastest supercomputer cluster at Harvard. And now in 2017, so now we are 2022, which I'm going to tell you a little bit, we have developed a new methodology, including methodology for causal inference. And now we can run the same data in 3 minutes. And so that also tells you in terms of how we are, the statistical community, and as well as the technological advancement is getting better and better and faster in analyzing this massive amount of data. When we published this paper in 2017, it had a tremendous amount of coverage, of press coverage. And first of all, because it was during the Trump administration. And so there was a tremendous resistance about lowering the national ambient air quality standard. And second of all, because of the enormous amount of health and environmental injustice, because we reported that these mortality risks were much higher for Black American. And so got the attention of Senator Booker, which actually has been really supportive of our research, for which actually collaborating with this office, we recently published last year an important paper in Nature, really documenting the environmental inequities in this country. But above and beyond that, one of the major criticisms of people that were, of course, opposed of the fossil fuel industry and the automobile industry about our work was the following. They said, well, you have all of this data, but you're analyzing this data using a regression model, and you're not showing any evidence of causality. How do we know it's air pollution versus could be something else? And so your findings are not valid because you cannot assess causality. Now, we all know among statisticians that when you're trying to analyze massive amount of observational data, you're never going to be able to exactly assess causality. You can do that in a context of a randomized trial. We will never be able to randomize elderly that are living in a clean air and randomize and sending them in breathing air pollution, right? So it's never going to happen. However, we also quickly realized that our community is very strong in the field of causal inference. And so a few years later in 2020, through the leadership of a former PhD student of mine, Zhao Hu, is a now postdoctoral fellow at Stanford, and a colleague in my lab, Danielle Brown, they led this extremely important follow-up study where we reanalyzed the entire cohort, but with methods for causal inference. What's the idea of causal inference and why we thought that it was very important? First of all, we updated all of the data up to 2016, and so we have like more recent information. So now we have over 38 million Medicare enrollees that were exposed at level below 12 microgram per cubic meter. So this is just an update of the data platform. And again, we have 1 kilometer to 1 kilometer exposure estimates to PM 2.5. We have temperature, we have data on socioeconomic status, we have data from the CDC and so on. So really massive amount of data. But one of the most important things is really to now account for confounding, not only using traditional regression model, which, by the way, there is nothing wrong about that, but we have to assume and hope that the model is right, but also using methodology for causal inference. So this is all of the list of the potential confounders that we need to account for it. So confounding is probably the largest threat to the validity of pretty much all of the most important conclusion from observational study that are informing policy. So whatever is the policy, but especially in the context of fossil fuel industry and in climate policy, because we cannot do randomization, the strongest criticism that we get is confounding. You don't know which is pollution, could be something else. Now, what this plot shows is that the levels of fine particulate matter in the United States, the level of ozone, and the level of NO2 that is traffic pollutant. On the right is a panel that shows, and I know you cannot see all of the variables, but that's okay, but it's a panel that shows the correlation between PM 2.5 and any of the potential confounders, like percentage of people that are underrepresented, socioeconomic status, poverty, education, and so on. So the bottom line is that you see that for some of these variables, there is a higher correlation between the pollution and the socioeconomic status. That means that if pollution and socioeconomic status are highly correlated, well, socioeconomic status could be a confounder, right? Could be something that if we don't account for it perfectly, we might misattribute pollution to poverty, right? And so instead of banning fossil fuel, we should also, by the way, it would be very nice to make people richer, but it's not the fault of the fossil fuel industry, right? So if you see correlation, that means confounding that we need to account for it. So we basically, what we did, we reanalyzed the data using adjusting for confounding, using standard regression approaches, but also using causal inference approaches. It's called using the generalized propensity score. Now, the idea of generalized propensity score is not new, and actually it's over 10 years old. But the implementation of how we match by the propensity score is something that we have developed as new. So the idea is the following. It's basically to find exact matches. So let me give you an example. So here is myself, Francesca, that lives in Cambridge. And I have my own body mass index, my socioeconomic status, my education, everything you can measure about me. And I've been breathing, being in Cambridge in the last several years, I've been breathing in an average pollution that is pretty low. Cambridge is pretty clean, maybe 5 micrograms per cubic meter. And, there will be some time fortunately, I'm still alive, but you will observe eventually time to that. Now, what you need to do, you have to find my counterfactual. How you find my counterfactual? You find someone else that is as similar as me as possible. Same age, they run the same number of marathons, has the same diet, they has the same socioeconomic status, but there is a difference. My twin sister is living in a geographic location where she's breathing much higher level of pollution. Now you see that the only difference between me and my twin sister is the pollution that we breathe. So if you can create, which with massive amount of data you can, if you can match every individual to his twin sister or twin brother, you can eliminate the confounding, right? And then you can compare the life experience between these twins, and knowing that then if the only difference between them is exposure of air pollution, then if the person that has been living in the more polluted area has a time of lives less longer than the one that has been breathing cleaner air, now you know that that is a causal relationship. Okay, that is really the fundamental idea. Then we can spend 5 hours and give you technical details, but it's really about finding matching. And so this is really the fundamental idea of a generalized propensity score matching. It's just that instead of matching for every single covariate, you match with respect to a score. So you calculate the score, a score of Francesca Dominici based on all of my life history and everything that you know about me. And then you find my twin sister based on this score. And basically what we do is we reorganize my entire database where every subject is matched to one or more twins, okay? And so the good news is that you don't need to do this by hand anymore, because Zhao developed a package, and actually it is publicly available, where you can actually create these matches by matching with respect to the exposure and matching with respect to the generalized propensity score. And so, you know, I'm giving you the link to the code and link to the paper if you really wanted to get really good understanding of generalized propensity score matching and causal inference, which is not only our contribution, of course, but it is a very wide area. Now, the wonderful thing is that after you have matched all of these individuals and find these individuals, all of their twins brother and twin sister, we break the correlation between PM2.5 and the confounder. So now what this plot shows, if you just look at the plot on your left, the red dots is the correlation between air pollution and any of the confounders before doing anything. And so you see that some covariates are highly correlated and there is confounding. The green dots are the correlation after we have found the matches, right? So because we match people with respect to their socioeconomic status and respect to their behavior, the correlation, the only difference between them is the different levels of PM2.5. And so there is no correlation anymore between PM2.5 and the confounders. So that's, even though it's not a randomized study, gets closer to a randomized study, because the goal of randomization is actually to break this correlation between, you know, what you want to compare, the treatment on the exposure, and the potential confounders. So we
ask you a question.
Oh,
so
sure.
What happens with the individuals that don't have the match? Does it happen?
That's a great question. That's a wonderful question. So in this situation, we bottom line, you know, the quick answer is that we drop them. But the good news is, because you have this massive amount of data, there are very few of them, right? Because if you think about, we have everybody older than 65. So it's really hard, you know. Now, it's also true that we don't match on in a very long list of covariates, right? So larger is the number of covariates, higher is the probability of matching. So in one hand, we have few of them because of the very large data, but it's also true that we have few of them because we cannot match on everything. And so one of the problem and the challenge and the limitation of what we do, which I'm going to talk later, it's a measure confounding, right? So I might have some confounders that I haven't measured, and therefore, I'm not going to be able to match, and therefore, my result could be biased. But that's a very important question. So the field of causal inference, there is, they call it the assumption of overlap, where it's really important that you meet this assumption of overlap. And what I mean by it is that you always find the matches. And then if you don't find the matches, then we call it trimming. And so basically we just exclude them from the observation. An alternative is, which we do, by the way, with regression, is to do model-based extrapolation, right? So we extrapolate what would have happened to the individual because we don't have a match. And again, there are hundreds of papers from the community that talks about how well you have to match, how close you have to match, with respect you have to match, and so on. But great question. So what this plot shows is now we reanalyze the entire cohort using the two traditional methods, the Cox model and now the Poisson model, and three methods for causal inference. And you see that when you look at the entire cohort, actually the methods for causal inference provide the results that are pretty similar of the traditional method. Now, we also reanalyze the data using only looking at people that were exposed at level below 12 microgram per cubic meter. And that's really important, I told you, because of their quality policy. Remember that if we found evidence of a mortality risk for people that are exposed at level below 12 microgram per cubic meter, then it's going to be direct evidence that the standard will need to be revised. And so we found that the fact not only are positive and statistically significant, but actually are larger. And also it's important to notice, for example, that using causal inference method, although the facts are larger and positive and statistically significant, are smaller than the one that we found initially with the traditional method. So that's really means that having a more flexible way, and this idea of matching that is so fundamental in the field of causal inference is so important to overcome a potential model misspecification. There is another very important area of research that is led by my colleague, not only Zhao Hu, but also Boy Ren, who's a faculty member, and Natesh Pillai, who's also a faculty member in the Department of Urban Statistics, where the idea is to use very flexible model to estimate the whole exposure response function. So the whole shape of how mortality risk change as we change PM2.5. So there is not only this idea of matching on using generalized propensity score. I'm going to be just very quick on a little bit of a technical detail of how we model this exposure response function. And the idea is really basically to estimate this causal effect of a continuous exposure, again, exposure to PM2.5, but could be to heat or could be to other environmental exposure, by really getting a full shape of the exposure response function. Now, the way that we did that in one of our work, and I'm not going to spend much time on all of these technical details, but basically is to using Gaussian processes. And Gaussian processes are a wonderful opportunity to model flexibly an exposure response function that will depend on the exposure level W and will depend on the covariance C. And then what we do, we use a generalized propensity score into the covariance function of the Gaussian process, so that people that have a similar propensity score, so people that are matched, have a smaller correlation in the covariance function of the generalized propensity score. I'm not going to go too much into all of this detail because I realize it's too late at night, but we reanalyze all of the database using this Gaussian process. And the reason why that's important is because if you parameterize your exposure response function using a Gaussian process, you can, and I'm going to spend some time about this picture, you can calculate the derivative of the exposure response function. So let me tell you really what it means. And I always like to explain even technical things looking at data. So let's go back to what's the fundamental question. The fundamental question is whether or not there is a level of PM2.5 below which there is no relationship with mortality, a safe level. Okay, so right now, The safe level for PM2.5 that is set by the World Health Organization is a 5 microgram per cubic meter. And the safe level that is set by the Environmental Protection Agency is a 12.5 microgram per cubic meter. This is the estimate of our exposure response function that we found by using causal inference method and matching and the migration process. And you can see that actually this relationship is pretty like almost linear, I would say. And you can see that there is an increasing level of mortality risk, even a level not only below 5, but by far below 12 microgram per cubic meter. When we estimate the derivative of the exposure response function, you see that actually there are 2 change points, one around 7 or 8 and one around actually 12 microgram per cubic meter. So what this is saying is, number one, the EPA level are not safe enough, because it would have been safe enough if below this level, you will have a curve that will be flat. That will be basically saying to you that below 12 microgram per cubic meter, you will not see an increase in mortality risk, which clearly you see it. The other important thing that our matching algorithm really worked, because you can see that after we have matched all our individuals with respect to this covariate, we have break the correlation. So basically what we'll be able to achieve is that the exposure response function is not flat, a level below 12 microgram per cubic meter. Is actually not even flat, a level below the WHO. And we can say that the interpretation of this exposure response function is almost, can say that there is a causal relationship, because we have been able to eliminate confounding, observed confounding. So again, for people that want to learn more, the manuscript is on the archive, is available here. You should absolutely feel free to get in touch with me if you wanted to have a copy. And also the code of everything that we are doing is available on the GitHub. So this is going to be really important, because basically what we are publishing and what we have published on Science Advance is basically saying that the current international ambient air quality standard for fine particulate matter are not safe enough. So as I mentioned to you, the WHO has already lowered the standard to 5, and the Environmental Protection Agency, the Biden administration, is considering revising the national ambient air quality standard as we speak. So this analysis is going to be really important. In fact, this was one of the press release. This was back in June, but they are actually reviewing all of the evidence as we speak. And in fact, they're also considering, as a very informative for their consideration, a potential link between exposure to fine particulate matter and COVID-19, as some of our study also have been providing evidence of that link. So for the last part of my talk, I just want to briefly also mention a second project where this was the coverage in the New York Times last summer, where we reported a study where we found a relationship between short-term exposure to PM2.5 and short-term exposure to PM2.5 from wildfires and COVID-19. We also published the first ever study on the long-term exposure to PM2.5 and COVID-19 mortality, and now we have a second study under review that overcomes some of the methodological challenges that we faced during the first study. So in this work, basically what we were very interested in doing the following. So last summer and the summer before, actually the summer before, December 2020, there was, this was before we had the vaccination. Some part of the United States, especially the west part of the United States, had really 2 tragedies going on. One was the COVID-19 pandemic, and 2 was a series of very extreme wildfires. So there is a lot of biological evidence, and I don't know how much you have been aware of reading, that exposure to air pollution can compromise the immune system, get very deep into our lungs, and now we know that it could exacerbate the adverse health effect of COVID-19. So I was able to lead this wonderful group of students and postdoctoral fellow. This is also was working together with Environmental Science Research Institute that are a geographic information system company that actually are the one that build the platform where you can monitor COVID-19 cases to really investigate and do a statistical analysis of whether exposure to wildfires increase COVID-19 mortality and deaths. So these are the two lead authors, Xiaodan Zhu, who is a data scientist at Esri, and Kevin Josie, who is a postdoctoral fellow in my lab. Again, we harness several heterogeneous data sources on PM2.5 and smoke density from satellite. We have a daily number of COVID-19 cases and deaths, temperature, mobility, and so on. So this is just a snapshot of the data. So we have data for for 69 counties, sorry, for 95 counties in the United States, in the states of Washington, California, and Oregon. And so for each county, so if you see here, these are the daily level of fine particulate matter, and with the orange are the day where wildfire was occurring. And so you can see that this level of fine particulate matter became extremely high on this level, on these days. With red dots are the daily number of COVID-19 cases, and with blue, with the dark dots, black dots are the daily number of deaths. So for each of these 95 counties, so we have PM2.5, wildfire data, COVID-19 cases and deaths, and many other variables. Now, from a causal inference perspective, it was very important to figure out which level of fine particulate matter were background level, so level that would have occurred anyway, and which level of fine particulate matter were attributable or caused by wildfires. So how did we identify that, right? So again, I like to show you things with data. So the blue dots are the level of fine particulate matter during the summer 2020, during the summer where we have the wildfires. The orange line are the days where we know a wildfire was occurring, okay? And we know that because we can look at satellite images, okay? The dark lines are the average of PM2.5 for all of the previous years in the same county for the years where we know the wildfire didn't occur, okay? So we calculate the excess, the extra level of PM2.5 attributable to wildfire by taking the difference between what was observed on a wildfire day and what we estimated to be using historical data, using previous years, knowing that wildfire in this year didn't occur, okay? So that is a pretty standard, I would say, counterfactual time series analysis. We built a pretty rich model, so because we needed to look at the level of PM2.5, not only today, but the day before and the day after to see whether it increased the risk of COVID-19 for the following days. So we call this distributed lag model. We have to build models for every single counties in the United States, sorry, in the west part of the United States, and then we need to pull the information across counties. So let me just go directly to some of the most important results and spend time a little bit with the figures. So on the left are the percentage increase in COVID-19 cases and deaths, sorry, the panel on the left is the percentage increase in COVID-19 cases, and in the right, the percentage increase in COVID-19 deaths for each single counties, for each of the 95 counties that is associated with the increase in PM2.5 for several days after wildfires. You see that there is a significant heterogeneity across counties. In some counties, we don't see an effect, or we see as actually a negative effect. In some counties, the one on the bottom, we see a huge effect. So for example, in Sonoma counties, we have the 10 units increase in PM2.5 for a few days lead to up to a 50% increase in COVID-19 cases. Now, we reported this work, and it was really important to also be able not only to quantify the burden, but also to visualize which county were more affected. And so we built a publicly available infographic, again, with Esri, where actually you can see, and again, you can go on the paper, all of the data is publicly available, this infographic is publicly available, and so you can see, because we really wanted to provide information to the public health community. So let me show you what this is. So basically, when you go on the infographic, you can click in any counties that was affected by wildfires. So for example, this is the Fresno County. So you click on Fresno, then you see the level of PM 2.5 during that summer. You see that in orange are the level of PM 2.5 that were attributable during the wildfire days. This is the daily number of COVID-19 cases. And then for each county, we were able to estimate the excess number of COVID-19 cases that were occurring as a result attributable to these wildfire days, right? So in Fresno during the summer, we have 1,600 extra COVID-19 cases and 131 extra COVID-19 deaths during these days of wildfires. And then you can click and you can identify data for every single county. Of course, please keep in mind that this was before vaccination. So I wanted to just wrap up to just say that I gave you 2 case studies and I gave you some intuition of a lot of the ideas and methodological work. But this work is hard because we are trying to inform extremely controversial policy regulation by looking at a lot of messy data, a lot of observational data. So there are so many unresolved data science challenges that we are trying to deal. And I am privileged to really work with a very large number of students and postdoctoral fellows. They're trying to sort it up and overcome these important challenges. Important challenge is the uncertainty, quantification, and propagation, right? So we estimate this exposure to our pollution. Therefore, there is uncertainty. We are statistician. We know this uncertainty has to be quantified and propagate. I think Olga gave me, asked me exactly the right question is about, well, what happened about non-overlap? Well, we have overlap because we only match with respect to a small number or a sizable number of confounders, but there could be unmeasured confounders. So if we were, for example, wanted to match with respect to the genetic history, we don't have that. And if we wanted to match with the genetic history, then we will have, many more unmeasured confounding and many more people that will not be matched. So there is another area actually of research that a member of the team, and Katie Hugh, is really using actually negative controls. Is thinking about outcomes that could not possibly be affected by air pollution and that could affect and could be considered as a negative control and therefore could be tools to adjust for unmeasured confounding. I gave you a sense of how much work there is behind the estimation of exposure response function, because its shape and the ability to say whether or not the curve is flat below a certain limit is really lead to $1 billion air quality regulation all in the United States and all around the world. I haven't had the chance to talk about heterogeneity, but that's really important. What I mean about is basically assessing with unprecedented rigor, vulnerability, and susceptibility. We know that some community experiences more harm due to environmental contaminants than others. And so that is really something that we are very committed. And then there is the area of reproducibility. It's really important to be as transparent as you can be in all of this, the data science pipeline, so then other people can reproduce the results. So there is a lot of work that I'm not going to have the chance to talk to explain it to you about methodological development in data science. And they're led by several of my colleagues and wonderful students. And so, as I said, having the reproducible workflow is really more important. I gave you a sense that there is a tremendous amount of work in data gathering, data harmonizing, data engineering, creating this data set, creating, thinking about new methodology, developing software and analysis. So we have really, I just scratched the surface, and I wanted to say that this work is really led by a wonderful community of people and colleagues. We have really, I will call it a consortium. We call it the National Studies of Air Pollution and Health. We have principal investigators from several other institutions. There are right now 15 postdoctoral fellows, 16 PhD students, master's students, and 7 undergraduates. So these are just some of the photos of the principal investigator that are in really contributing. I wanted to really acknowledge Danielle Brown, who is really the mind and the energy behind a lot of what we do, as well as Rachel Nathery. And a lot of our PhD students and postdoctoral fellows that Robbie Parks from Columbia, just like yesterday, published a really important study on JAMA looking at mortality risk and cause-specific mortality from tropical cyclones using some of the data and some of these ideas. So more and more wonderful students and colleagues. And so basically, I wanted to conclude that by the steps that are needed to mitigate climate change in the future are really substantially the same as those to reduce the burden of death and disability to the air pollution in the present. And so really the importance of cutting back on burning fossil fuel and biomass. And so in the meantime, we are seeing that the tremendous technological advancement and our ability to develop a methodology in machine learning and data science, really it's allowing us to be more scientifically rigorous in providing evidence that really matter for policymakers. And so I think methods for causal inference have been around for a very long time, but by no means I'm the only one. There are hundreds and thousands of people. And I also wanted to acknowledge, for example, that the Nobel Prize in Economics given by Guido Imbens, it was indeed due to his tremendous contribution together with Don Rubin in advancing the methodology for causal inference. So thank you so much for your attention, and I will really love to have a conversation and discussion and address any question you might have.
Thank you so very much for the fantastic talk. This is fascinating. This is really wonderful. So we do have time for questions, and I hope there will be questions in the audience. And maybe while we're waiting for questions, I have a couple, if you don't mind, if I can ask. So one kind of more technical and one not so technical. So on the technical side, just for the causal inference specifically, there are of course different schools of thought, right, in terms of like how you do this. And some people may be compelled to draw a DAG, right? So direct acyclic graph, and kind of specify some models on that. And it has some advantages, maybe for interpretability, right, or transposability. So in this particular example, so what was the reason that you went with the score-based methods rather than like DAG-based methods? How would you think that would compare?
Yeah, so first of all, I don't consider drawing a causal acyclic graph like an alternative. It's actually, we did draw basically a high level description of what's happening, right? So drawing a DAG, a direct acyclic graph, is a way basically to crystallize your assumption and how the confounding might occur. In this way, we know, we have hypothesized that, right? So because we have the air pollution is affecting health, and then we have several other pollutants and socioeconomic factors that are the confounder. Of course, the direct acyclic graph can be, when you're thinking about time varying data, much, much more complicated, right? But it's not an alternative, because actually in the school of thought, what they say is that, yes, you draw the DAG, you identify, which is basically what we did, then you identify the parameter of interest that you wanted to estimate, and then you are estimating. Now, the way that we are estimating, we are using the school of thought of the potential outcome and the propensity score. Now, other people might want to have marginal structural model or different approaches. In our context, I think it's really different than what they call it is a dynamic treatment regime. So, I think we could have a more, a broader discussion, but I will not consider our approach as a complement, as like an alternative. Now, there is another school of thought, which is actually using the data to discover your graph, to basically discover the causal structure. I think that that approach will not work in this context. And the reason is because the health effects associated with air pollution, fortunately, are very small, right? So the predicting power of pollution on health, it's not strong compared to the other confounders. So there is not such a strong predictive power to be able to discover the DAG from data. So you have to hypothesize what is a reasonable DAG and then do the estimation.
Makes sense. Oh, very interesting. And can I ask you another question, maybe more like on the communication side? So when you talk about this, the Congress representatives or some policy makers, so what is the level of technical details that like resonates? So are they essentially looking for sound bites, or can you talk about counterfactuals, and like really of specific mathematical concepts?
I've been, so first of all, it really depends on the setting. But for example, with Cory Booker and his staff, not Cory Booker himself, but his staff are very, very skilled and proficient in causal inference and data science. And so actually, and I think the interacting with this office has been extremely helpful to us because help us to be more sharp in terms of the question that we want to address. But they've been very, very, very interested. So there is actually a level of understanding and proficiency. And I have to say that unfortunately with the COVID-19 pandemic, people are becoming, more knowledgeable. Now, there is another setting which is actually really hard, which is when you are dealing with paid consultants by the automobile industry or fossil fuel industry. They're trying to discredit your work using technical terms, but not being really be aware about what the technical term means. And that's actually, it's really challenging because there is, they tend to infuse the conversation with technicality with the specific purpose of confusing everybody, right? And so it's amazing, like, unfortunately, in our discipline, how easier is to confuse compared to give clarity, right? So so you find yourself, I found myself on this conversation where on the surface, it sounds at a high technical level, but the reality is they are using words to create confusion. And so that actually is the most challenging part. It's not providing clarity and explaining, but it's really making sure that the purpose of the conversation is not to leverage statistics word. And so actually causality, it's a classical example, right? It's an example of saying, well, in a very high level in this context and say, well, you didn't, you're not showing causality, so everything you're doing is wrong. Well, in statistics, even when we're feeding a regression model, yes, we are not assessing causality, but we are adjusting for confounding. We are not just reporting a correlation, right? So they use some of our word to, unfortunately, for not good, good purposes.
Very interesting. Thank you so much. Well, that's fascinating. Maureen, would you like to ask your question or would you like me to read it? Okay, so Maureen is asking, how did you select your important covariates by science? Did you consider use the machine learning approaches to select covariates? So I guess by science, Maureen meant like by the background knowledge.
Yeah, exactly. Right. Yeah, exactly. So it's mostly from the background knowledge plus everything that we can measure. So the good news is that because the data are so huge, we don't need to worry about, having a parsimonious model, right? We can adjust for as many things as we want. So, but also, I mean, I think that, when you're thinking about what can confound the relationship between environmental exposure and health, mostly behavioral factors, smoking, alcohol, previous diseases, and socioeconomic factors, right? These are the ones that we really pay attention. Now, we did not use machine learning to select the confounder. However, I'm glad you asked this question, because we did use, and we are using machine learning to identify communities that are more vulnerable to air pollution and climate change. And machine learning can be extremely valuable for that. So instead of saying, for example, are older people more vulnerable or not, and test the hypothesis, we have trained the machine to tell us what are the characteristics of the people, which could have multiple concomitant factors that makes them more or less vulnerable to the health effects of air pollution. So machine learning has been now used for that. And by the way, some of the work was originally published in the Proceedings of National Academy of Science by colleagues at Stanford, Susan Eadie and Guido Imbens. And so then we are now building on that work.
Thank you so much. Okay, Xiaodong Zhu. So would you like to ask a question? If not, I'm going to go ahead and read it. Hi, Professor Dominici, congrats. Is there any explanation for the little bump in mortality rate plot when PM 2.5 is around 13? Does that indicate any missing confounding? So fairly specific.
It's a great question. That's a really smart question. And I don't know. I don't have the answer. I think that this is something that we are looking more. It could be that I don't know if it's a missing confounding, but it could be that there could be also some effect modification. So stay tuned. I don't know, but it's a great question. We're looking into that.
Thank you so much. Let's see. Anybody else would like to ask anything? Okay. Maureen once again. So let's see. Could one also consider evaluating air pollution thresholds by region rather than on the national level?
Yeah, it's a great question, Maureen. So yes, we can, and we should, and we will. However, so yes, absolutely, and I think that this is why I think everyone is interested in interrogating this data. There are so much work that can be done. Now, the reason we haven't done it yet, or it was not the top priority, is because of how we have the law in the United States. And the law is to set a national ambient air quality standard that is the same for everybody. And so, I think what we want to do is first to make sure they make a decision about this law, and then providing further evidence, because we will expect, and I think that's going to be a fascinating analysis, that there will be different threshold in different community. So, so I think, it's an important analysis to do from a scientific viewpoint, but it cannot directly inform policy, because they're going to just, the national ambient air quality standard is one. Although it's interesting, you never know, because it's true, for example, that California is setting their own standard in a different way. So it's a great point. I think it's something we should definitely pursue.
Thank you. I think I heard somebody trying to speak through the microphone. Is there another question?
Yeah, very nice talk. One of the things I've always a little bit concerned about is the model building aspect when using propensity scores. And the problem with propensity scores especially when using logistic regression, is that it's an issue of collapsibility or non-collapsibility bias. And if you have a weak confounder, that weak confounder can influence the adjusted variables when they probably really shouldn't be. And that's a well-known aspect of epidemiology with the lack of collapsibility for logistic regression. And generally, it's always a good idea to try to create your propensity scores with something that's a marginal estimate, like log binomial or negative binomial. That tends to minimize any risk of the collapsibility issues. The other issue is in building the models is over adjustment and unnecessary adjustment, just like building any regression type of model. And there's some subjectivity and whatnot, and that one person can build a model with certain variables and then a different model with other variables. And if you do have the overmatching issues that come into play, it can change results. The saving grace, though, and I think with your research, it's very credible because the results match up fairly closely with this traditional Cox type of models without using propensity scores. So I think that's important. But that's my one sort of, I guess, caution with propensity scores is if folks can build those propensity scores using log binomial regression rather than logistic regression, that's a preferable way of doing it.
Well, thank you, Jimmy. I wanted to clarify that our exposure is continuous, so we don't build a propensity score using logistic regression, but we build a generalized propensity score, so using normal models and actually using machine learning model. And also, I think is important.
Oh yeah, that's much better.
And also, but your point is absolutely well taken. And also, when we adjust for the propensity score, we don't include the propensity score as a covariate into the model, but actually we match. We create a new data set by matching with the propensity score, and then when we estimate the exposure response score, but that's done completely non-parametric way, right? But your point is absolutely well taken, and that's also why we have done it this way, because we really wanted to avoid these non-collapsibility issues, so that are really something to keep always in mind in this type of application. So thank you for pointing it out.
Thank you so much. So Richard is asking a question. Could the people that were affected by fires increase their COVID infection because they were displaced and have to move and interact with more people instead of socially distancing at home? The hypothesis of weakened immunity due to pollution does make sense too.
So great question. So, and this goes into the why, right? Because you see, like, if this is happening, so is it really the wildfire, or is it because the wildfire changed the behavior and the mobility and that lead to more COVID-19 infection? So I cannot say to you, I cannot say in conscience that I can rule out that possibility. However, we did adjust for mobility in terms of trying to see whether this community that were affected by wildfires at different level have a different degree of mobility. It's by no means perfect. So I do think that could have been, what you're raising is definitely a possibility. And yes, I mean, I think the weakened immunity is something that now has been established. And I think that is really, it's interesting because my sense, and we'll see what's going to happen with the Environmental Protection Agency decision, but my sense is that they're probably, if they're going to lower the National Ambient Air Quality Standard, I think that these COVID-19 studies and now the biological plausibility that PM2.5 weak the immune system. And so it makes us more susceptible to the next pandemic. It's going to play a huge role into the decision. But I think what you're raising is really another real important area of research that is completely unexplored. Because everything I've been saying to you, regardless how much data, how much fancy, right? The only thing I'm telling you is that PM or wildfires are bad, okay? But I'm not telling you why, above and beyond the clinical, but how the behavior of an individual is changing as a result of the wildfires, and whether there is a direct effect or is indirect because the behavior is changing. There is wonderful work out of Stanford that is going to come up pretty soon that are harnessing data from Twitter and Google searches and actually from mobile phone that are trying to characterize how our behavior change in the results of these wildfire events or tropical cyclone events. So then we have a better understanding of the cascade, all the causal consequences. So that's, it's another really interesting area of data science that I think is really very promising.
Thank you so much. We have two more questions. So Enoch is asking, have you thought about looking at other industrial pollutants like sulfur dioxide? There is recent data coming from London that shows that sulfur dioxide is strongly associated with all-cause mortality 4 decades later after the London smog episode of December 1952.
Yeah, it's a great question. So yes, in terms of that, when I had the chance to go into all of the details, but when we estimate the exposure response function, we not only estimate it for PM 2.5, but we are estimating it for all of the major primary pollutants. So, I show the results for NO2, which is the traffic pollutant, and ozone, but we also have and should analyze it for SO2. In addition, we are collaborating to develop machine learning model to also estimate the exposure to all of the chemical constituents of PM 2.5, and SO2 is one of them, to really understand what is in the PM 2.5 that really make you sick, right? And so, for example, right now, when we say we're going to lower the national metal quality standard for PM 2.5, it's going to penalize, I would say, equally, for example, the automobile industry and the fossil fuel industry, for example, the power plants, right? This is going to lead to all a cascade of intervention for power plants and cars. Now, let's say that is really only NO2, the traffic pollutant, that make you sick and not the power plants. So then you could target more the cars versus the power plants, right? So we're really trying to not only estimate the effect of PM 2.5, but by estimating the health effect of the sources of PM 2.5. So then when there are regulations, they can be a little bit more targeted.
Thank you. Okay, and let's see. Jinyoung Lee is asking, well, first, thank you for wonderful lecture, Dr. Dominici. I have a question. Is data you use cross-sectional data or panel data? Also, if we have national public health data we can access instead of Medicare data, how could we extend our study to the whole population?
Yeah, it's a good question. So I will consider the data, the panel data is a time varying data. So we have repeated the measurements over time for all of the air pollutants and for all the health outcome. So it's definitely not the cross-sectional data, although, you can analyze at a single time point as a cross-sectional data. We don't have a national public health data. And if you do, let me know. So my understanding, and so the Medicare claims are probably the most complete data on claims on mortality and cost-specific hospitalization. And by the way, you can purchase doctor visit for a representative population, an almost complete population of people older than 65. We have data cost-specific mortality for all age group from the National Center of Health Statistics. But the challenge there is that we have the place of residence at the county level. So then when you're trying to link with air pollution exposure, you can only link to county level data. So of course, we also have Medicaid claims, which we are analyzing, and Medicaid claims are all ages, but for people older, for people that are eligible to Medicaid. And so the challenge with that is that the eligibility criteria change from state to state. But if you have a better data set out there, please let me know.
Okay, so let's see, anybody has any more questions? It's a unique opportunity to ask Dr. Dominici anything you would like to know.
I just
Yes,
have a
please.
question. So my name is Enoch. I am a Marie Curie Fellow from University of Glasgow. My question is for your linkage, for pollution linkage, how far back do you go? Do you do a historic pollution linkage, or do you mostly focus on short-term exposure?
That's a great question. Thank you. We focus on both. So we both do studies of short-term exposure. So for example, we ask whether an increase in air pollution level yesterday or 2 days before increase your hospitalization risk today. But also we look at chronic exposure or long-term exposure. And so basically the idea is that we have complete data starting the year 2000. So every year we have new people that enter into the cohort. And so we then can link back to their exposure up to several years before, right? So for example, if you become eligible into enter into the Medicare, let's say in the year 2015, I have exposure to air pollution up to 2000. So I can calculate your exposure to PM 2.5 for the previous 15 years. The other thing that I didn't mention is that it's not perfect, but as a surrogate, we also know whether or not people move. So we have done some study that if you enter in the cohort in 2015, let's say, and then in 2017, you live in New York, in 2017, you decide to move to Florida. Through the claims data, we can flag that. So in 2017, then I can start looking at your exposure in Florida and not in New York anymore.
Wonderful.
Oh, that's great. Thanks.
Thank you for your question.
Okay, so let us thank our speaker once again. Congratulations, Dr. Dominici, with the award. It's a great honor for the chapter as well. So we are very happy to have had a chance to hear from you. So please do join us in the future events. Please become chapter member. I think it's $5 for students and $10 or something like that for non-students.
Count on it.
And please, if you are in an academic environment, please send your students. If you are in a company or in industry, please direct your colleagues. It would be wonderful to have more members and more participants in different events.
Absolutely.
Thank you so very much. And I hope to see you next time.
Absolutely. Thank you.